of modes outside the horizon of a black hole. So let's consider the operator n, which is defined as the dagger v for some particular frequency. So this operator counts how many particles we have on the exterior of the black hole, and as we argued yesterday, this has a thermal expectation value, it's thermally populated. But this operator has the property, because this guy has frequency omega, and this guy has frequency minus, this is a dagger, so effectively it has frequency minus omega, it has frequency omega, so this operator has the frequency 0 in some sense, or in other words, this operator commutes with Hamiltonian. This statement is not exactly true because it's true only in the larger limit, but for the purpose of this argument, we can take the larger limit, and if you work a little more carefully, you can convince yourself that the one-over corrections do not invalidate the argument that I'm going to present. So then what we're going to do is we will consider an operator which corresponds to what the influence observer measures. So that would be another operator for particles in a particular mode of the field that the influence observer will detect. It will be a projector, which is 1 if the horizon is smooth, 0 otherwise. So it will be some observable for the influence observer. Let me call that observable A. So this is something that the influence observer will measure. And this observable will indicate whether the horizon is smooth or excited. Now, we will argue that there is a contradiction between the following statements. For typical states, which means for most black or microstates, A predicts a smooth interior. So let me make it a bit more precise. So let's say that we declare that if the expectation value of A is 0, then the horizon is smooth, or there are no particles in a specific mode. And if this 1, then there's an excitation. So the first requirement is that for typical states, we want the horizon to be smooth, which means that the expectation value of a typical state has to be equal to 0. On the other hand, we just argued before that for eigenstates of another operator of the most outside the horizon, the expectation value of A will have to be equal to, let's say, 1. Right? If you go back to the enclosed vacuum, and if instead of this superposition you consider, just one element where the number operator on the right is an eigenstate, that's an excited state. There are particles across the horizon. So if you point to an eigenstate of this mode n, the influence observer will detect some particles. Right? So we have these two conditions which seem to follow from effective theory and from our desire to demand that the horizon is smooth for typical states. And these two are in contradiction for the following reason. If this equation is true for typical states, then it means that if you also compute a trace of this operator A over the ensemble of states of given energy, so let's introduce the macrocanonical density matrix here for states of energy between E0 minus delta and E0 plus delta. We consider all possible microstates in that energy domain, and we compute this expectation value. According to the first equation, this will be equal to 0, or at least approximately equal to 0. However, because the Hamiltonian commutes with another operator in the exterior, these two operators commute, this means that you can find simultaneous eigenvectors of the two operators. You can diagonalize them simultaneously. In other words, if you look at the subspace of states within that energy range, you can select the basis in that subspace where the basis elements are eigenstates of the operator n. I mean, a trace you can evaluate in any basis you like, right? So here we're thinking about perhaps the basis of energy eigenstates, but this trace will be equal, you can equally write down the same trace in the basis of eigenstates of the operator n. So this is another variation of sum over these eigenstates. And pi. But in each one of those, the expectation value is 1. So then this will be equal to 1. So we have a contradiction again. So this is a good argument which indicates that something is strange about this algebra, and it may be very difficult to construct this operation between in the conformity theory. Finally, there is let's say, a more general intuitive argument, which is the following. If this B tilde were some normal fixed operators which are the same for all microstates, then we would be able to think of them as representing the tensor factor in the Hilbert space of the CFT. So the Hilbert space of the CFT would consist of a sector representing the operator B outside the horizon, so then B tilde inside just behind the horizon, and perhaps other stuff which are not represented in the bulk in a simple way. But then what we want for smoothness of the horizon is that these two tensor factors have to be entangled in a very precise way. As I explained yesterday, we don't just need a certain amount of entanglement, we want even the details of entanglement to be precise, right? For instance, I remind you in Minkowski space, if you modify the state by some traces here, you do not change the amount of entanglement, but you do change the details, and then the state becomes excited. So if we want the horizon to be smooth, we need to have a specific and precise entanglement between these two sectors of the theory, and this has to be true for typical states. This is extremely counterintuitive. If you take a complicated chaotic system and you divide two parts, and you take a typical state, a random state, why would you always have the same pattern of entanglement between two subsectors? It sounds like it's going against our intuition from statistical mechanics. Okay, so this is another argument, and all of these arguments indicate that a big black hole in ATS may not have the smooth horizon, and I want to emphasize that even though this is not the original problem that we started with, I mean, we started with an information paradox in class phase, and now we went into a paradox about the horizon of an ATS black hole, a big ATS black hole which does not evaporate. However, one important point is that this formulation is perhaps a more well-defined version of the paradox, because it's phrased in the context of the CFT, separation about operations of conformity theory, and, well, at least in my view, it's a very precise formulation of the paradox. So, before I go on, are there any questions? Yeah.
Just to jump in, if I could address the last one, they have the same entanglement.
Yeah.
I wouldn't have said that there's a puzzle on some for something particular type of attack. What is it that he information I wanted to go through these states? I would have said that one of the particular states is that particular state.
Yes, I don't see how to break the symmetry between those states based on some general argument. I mean, if you fix operators, if these operators are fixed a priori, if they're fixed, then of course they select one particular state. If you want the other state to be smooth, then you will have to introduce some phrases here, and, but I agree that there's no invariant way to select one of those states. But for me, that's not really a problem because, as you know, I'm going to argue that the operators are actually selected by the entanglement. So no matter what the state is, the operators will be adjusted so that that state is a vacuum. Any other questions? Alright, so these are the paradoxes, and let's try to see how we can look for a way out of these problems. So now I will present a proposal for defining the Rotundas based on some work that I did with Surratt. And let me start with some intuitive introduction, and then I will give some more detailed equations. So the first observation is that, as we discussed yesterday, if you take a conformity theory microstate psi, which is dual to black hole, then we expect that at least many times it will thermalize and equilibrate, which means that correlators of single trace operators on the state are very close to semi-correlators. Now, this statement is true for a small number of operators. If you start multiplying many of these guys together, and if you fine-tune them in a very clear way, you may be able to find deviations, and that's why you can detect that the state is actually pure and not thermal. But if you restrict yourself to simple correlators, then this is a good approximation. Now, let's ask intuitively, why is it that how can it be that an isolated quantum system thermalizes? Right? There's no heat bath. Now we're talking about an isolated CFT. There's no heat bath, but it nevertheless thermalizes. So the reason that an isolated system thermalizes is because, in some sense, part of the system plays a role of a heat bath for a certain class of observables, which are usually the observables that have a nice thermodynamic limit. So whenever we want to talk about thermalization of a pure state, it's important to consider the notion of a certain class of simple observables. We don't want to talk about an observable which is the correlation function between an Avogadro number of particles in a room. That observable may not thermalize. We want to talk about simple observables, like the density of the gas in the region, and so forth. And in this Larsen-Gibbs theory, there's a very natural way to define this class of simple observables by considering the sector of low-conformal dimension single trace operators, which represent basically a very small part of the Hilbert space. I mean, we know that the entropy of the states are like n squared, so the quantum of microstates are many of them, but there's a hierarchy between the number of those states and the number of light operators that you can write down in the Larsen conformal theory. So we concentrate on these light operators, and we think of them as defining a small algebra where you can take these guys, you can multiply them together, you can take linear combinations, but you should not multiply too many of those. So the number of factors in this product should not scale with capital N. So, of course, if you impose this cutoff, this is not really an algebra. It is a set of observables which behaves like an algebra in a limited sense, as long as the number of factors in the product is small. But strictly speaking, mathematically, it's not a complete algebra. I think this is not a problem. I mean, also when we talk about Larsen factorization in Gibbs theory, we have the same issue. Larsen factorization holds only if you multiply a small number of operators. If you multiply many of them, it may break down. And if you want to know the precise cutoff, that may be a little bit tricky. But for everything we're going to say, this issue, for most of the things I'm going to say, this is not a problem. Yeah.
Is this algebra characterized by the equation that's at the top of the slide?
I will define it in the two slides from now. So the point is that if you take a small algebra and you probe the state, the pure state, it will look like a thermal state. So even though we are in a single conformity theory, in a pure state, there's no heat bath, there's no second conformity theory. When you compute correlators of the small algebra on the step psi, as I just argued in this equation, these guys are very close to the thermal correlators. And perhaps you know that thermal correlators can be exactly recovered by introducing the second fictitious copy of the theory, and then placing all these operators on the second copy, on the right side. So the left side here, in some sense, is a fictitious copy, which you can think of as representing the heat bath. And the point is that if this algebra is acting on one of the copies, and this state is entangled, so this means that the small algebra probes the state psi, which is a pure state, as if it were an entangled state. So the state is not entangled, it's a pure state, but you're probing the small algebra, so you don't have access to the entire part of the theory, and that's why the state seems to be entangled. Intuitively, what this means is that you have all the n squared equal to freedom of the conformity theory, which plays the role of the heat bath for the small algebra. And now, the intuition is that these operators of the small algebra represent what's happening outside the horizon. So these are the B's. And the big tildes are whatever the B's are entangled with. So the big tildes are excitation of the heat bath. And they're selected by the fact that they're entangled in a specific way with the B's. That's the intuition. Okay, so let's try to now make it more precise and see how we can write down some equations which will define the operators. So let's also get some intuition from the bulk. So we have a black hole in the psi and an observer in the bulk, and this observer wants to do various experiments. But these experiments have to be described within effective theory, so this is not too complicated. Now, if you want to describe experiments within effective theory around a particular black hole microstate, then you don't need the entire Hilbert space of the CFT, because most of those experiments will take place in a subspace which is characterized by this contraction. If you take the black hole microstate, you take the state where you act with one operator on this black hole microstate, 2, 3, 4, up to a certain number of these operators, and you take the linear combination of all of those guys, where again we demand that the number of insertions n should not scale with capital N, and at this point are not too spread out in time for some technical reasons I will mention later. So this defines the subspace of the Hilbert space, and the claim is that if you want to study effective theory in the bulk, for example, if you want to know what happens to an observer pointing to the horizon, you can phrase the operation purely within this subspace. You don't need the entire big Hilbert space of the CFT. So let's now go back to the boundary and define the small algebra more precisely. So we have some quadrilateral plasma microstate, and this field phi in the bulk is related to some single place operator O. And then we have to impose some limitations. So here we see the ADS space. We select some bands in time of length capital T. I think I want this capital T to be at least a few times the scrubbing time. Maybe slightly longer, but it will not be necessary for the experiments we'll discuss to take it to be extremely long. We also have to impose some Euclidean regulators, so we don't want to allow these operators to come too close to each other. And we define this small algebra as the linear span of single trace operators inserted here, anywhere. Well, we have to regularize it, but anywhere in this band. The product of two of them, three of them, up to a number which can be as large as you like, but it has to be much smaller than capital N. So this defines a small algebra, and we also define a small Hilbert space as the linear span that you get by acting on the step psi with small algebra. And as I already explained, a simple effect filter experiment in the bulk for a given plasma microstate are going to take place within this subspace of the CFT. So these interior operators with tilde, I'm going to define them only on the subspace. I'm not going to tell you what they are on the orthogonal complement because I don't care what they are. If I want to study an experiment for a particular plasma microstate, then I only need to know how this operator acts inside this subspace. Now this object is very similar to what was later called, let's call it called subspace. So it's very similar. You start with the state and you consider all possible states that you get by acting with single operators on that original state. So sometimes I will refer to this as a closed subspace or small Hilbert space. Now the important point is algebraic point is the following. Even though we define this subspace A of psi by acting with single trace operators on the same side, or equivalently, we define it by acting with a field outside the horizon. Because of the entanglement, it is a fact that actually the Hilbert space already contains states where the black hole interior is excited. I never acted with an operator in the interior. I only acted with operators on the exterior, but nevertheless, the states that you get in that way can also be thought of as excitations as states where the interior is excited. Now, if you find it surprising, actually you should know it's very standard, and you can work it out yourself here as an example using Minkowski space. So take the Minkowski space in regular coordinates, and it is a theorem, the Richter theorem, which says the following: if you take this quantity theory in the ground states and you act with operators on the rank bench, you generate the full Hilbert space of theory, or a dense subspace.
That assumes the horizon is smooth, or is that
the last statement I made, the last statement I made was a statement of quantum field theory, so it does not, which horizon? You are talking about the non-gravitational quantum field theory? But I said this is a statement of the ground states, of the Lorentz invariant ground states of relativistic quantum theory.
So you assume that the horizon is just like
I assume it. No, I don't think I assume it. I mean, you prove it, right? You can prove it. I'm talking about a non-gravitational theory now. That's the Minkowski vacuum, right, of the quantum theory. I mean, if you take the Minkowski vacuum, there's certainly no firewall there, right?
Right, but you're assuming that you want to identify this with the horizon.
Okay, there are different statements. One statement is purely in quantum theory. There's no doubt about the horizon. It's certainly smooth, right? There's no firewall. And the statement in quantum theory is that taking the Minkowski vacuum of a quantum theory, it can be free, it can be interacting, but it has to be Lorentz invariant and so on and so forth, and act on the Minkowski vacuum with operators which are localized in these ways. So the theorem is telling you that by doing that, you can generate the full Hilbert space of theory. So you don't need to act explicitly with an operator on the left in order to create an excitation here. You can create an excitation here by acting with an operator on the right. For those of you who are worried, who have not seen this theory before, and you're worried about causality and how can I construct something far away by acting here, the resolution of this main paradox is that if you really want to know what you can actually do in a lab, what you can do is you can act with unitaries on the right. You cannot act with Hermitian operator, you can act with a unitary. And if you act only with unitaries, then you cannot modify the space-time in this region. So if you only act with unitaries, then you cannot reproduce excitations in this region. However, if you act with arbitrary Hermitian operators, then you can. Alright, so this is all very standard in quantum theory, and what I'm saying is that the same thing applies locally near the horizon of a black hole. So from the point of view of the bulk, if we act with operators here, we're actually generating states where there are excitations in the interior as well. You can get all types of states in this way. So a state where you have one particle behind the horizon is already contained in the set that I defined by acting with operators in the exterior. I don't need to add it explicitly as a new state, it's already there. In the same way that if you take the Minkowski vacuum and you act with operators on the right, you generate a full Hilbert space. Okay, so this space, this called subspace or small Hilbert space, already contains excitations, states which have excitation in the interior, and these are the excitations that you could get either by acting directly with the dagger, between the dagger on the same side, or by exploiting the entanglement, you could get them by acting with something on the exterior. Yeah.
I guess the statement that you're applying the Richter result to indicate inside outside.
If you want to be strict, no. I don't want to do that. I just define this set for now. I mean, we can think intuitively that this is what we're secretly doing, but I don't assume it here. I don't assume there is single theorem. I don't assume anything.
I guess another saying that probably we know there's no firewall.
Oh, we don't know. We don't know. So
there is no that.
Well, so at the algebraic level, the only condition that I need is that if you have the small algebra on the same side, you do not get zero, right? You cannot annihilate the state with a small algebra. If that is true, I can define some operator tilde which you can use to reproduce a smooth interior. That can always do. Now you can ask a further question, which is how do we know that this is a formal construction, right? How do we know that this is what actually the informing observer we measured? That I'm not able to answer. So the only thing I would say is that there is enough space on this Hilbert space to define on that Hilbert space a set of operators tilde which have the right properties so that they can be represented as the operator behind the horizon. So I said that we define it just by acting with operators outside the horizon, but as we'll explain a little bit, the Hilbert space that you get in this way is large enough so that you can actually define a new second copy of operator with the tilde acting on the same Hilbert space and at the same time commuting with the B's or the O's. I'm sorry, so to get confused in the slides, whenever you see, most of the times, B you can interchange with O and B tilde by O tilde. Sometimes I write B to emphasize the bulk picture, and sometimes O to emphasize the CFT picture, but I mean, sometimes I mix them up, so B and O, B tilde, O tilde can be interchanged. So you can ask the question now, one moment, what are you saying here? I mean, can you do this for every state? For example, you can take the ground state of the CFT and play some game and then define a second copy of the operators. That would not make sense, because if we're in the ground state, we just have ADS, empty ADS, there's no horizon, there's nothing behind anything, so we'll still be able to do this, what I'm planning to do for an arbitrary state. So there must be something special about states representing black holes in the bulk. And this is a special property that I will explain. So so this equation, and this is the answer. The answer is that if you take a typical black hole microstate, psi, you cannot annihilate it by operators in this small algebra. So if you take a black hole microstate and you act with a single place operator, or two of them, or three of them, or a small number of those, you will never be able to annihilate the state. This is different from the vacuum, where the vacuum you can annihilate. It's different from a state with 5 particles, because that you can annihilate with a reasonably simple operator. But if you give a big black hole and you want to write down an annihilation operator for a big black hole, that's not possible unless you use very complicated operators. So I'm trying to argue in the next few slides that the fact that you cannot find annihilation operators has very important algebraic properties and implications for the representation of the algebra A on the Hilbert space of this code, the representation of the algebra on this code subspace. So in particular, there's some qualitative difference when we compare this construction in the case of black hole microstates to the case where psi would be the vacuum. And just to give you some intuition why this algebraic property is important, the fact that we cannot annihilate a state can also be understood as a statement that psi appears to be entangled when you probe this small algebra. So the fact that you cannot find annihilation operators for your system basically is telling you that your system is entangled with something else. If that's not clear, you can consider some simple toy models. Take two spins. So let's take two spins in an entangled state. A, B, A, B. Now, can we find annihilation operators for the state? So can you find annihilation operators in the small algebra which annihilate the state? This one here. So if you act on the first state with a raising operator for the first spin, you're going to get 0, right? So if you act with S plus A on the state, this is going to be equal to 0. So you can find an operator in the algebra of the first spin which annihilates the state. In this case, it doesn't. If you act with this operator on the state, you kill this component, but you don't kill the other one. You can convince yourself that this is true for any possible combination you can write down. For instance, if you act with S plus A squared, you can annihilate the second state as well, but this doesn't count because this operator is identically equal to 0 on all states, right? So the condition that we have is that this state should not be annihilated by non-vanishing elements of the small algebra, right? Another relevant example is that of Rindler space, where the Rindler theorem is also telling you that you cannot find annihilation operators localized only on the one with the wedges. I mean, you cannot find an operator which annihilates the vacuum, the Minkowski vacuum, by acting only on one with the wedges. That's a consequence of the entanglement, right? If you act a lowering operator on the right, you just lower this guy, but this guy is heavily populated, so it doesn't give you 0. And again, so we see a connection between the algebraic property that we cannot annihilate the state and the fact that there's some entanglement in the system. Alright, so let's proceed. So algebraically what we have is an algebra acting on some Hilbert space, and it has a property that the algebra cannot annihilate the state. So sometimes this is called that psi is a cyclic and separating vector. And when you have a situation where you have an algebra acting on a Hilbert space with a property that there's a cyclic and separating vector, there is a nice mathematical theorem which tells you that the representation of this algebra on the space is reducible, and you can find a non-trivial commutant for the algebra acting on the same space. What does commutant mean? It means a set of operators which commute with all elements of the algebra. Moreover, even though I haven't written here, this theorem tells you that the commutant is isomorphic to the algebra itself. So you will find a second copy of the algebra which commutes with the previous copy. And both of them are acting on the same Hilbert space. There's yeah.
You can tell me yourself. Well, now if you go away from the thermal state, and for example, I can build a little refrigerator that I put somewhere outside of the black hole and make sure that some effect is not excited, and I can actually annihilate it with a simple operator. I still wouldn't want to say that there's a firewall because of that.
Yeah. So, that is the limitation of this construction that I'm presenting, which is the following. I don't know how to do it in one shot for all states. I know how to do it for equilibrium states. And taking that answer, I can slowly build up the definition for the state that you're talking about. But you may not be entirely satisfied by that, because it would be nicer if you could have one equation which works for all states at once. So these equations that I write down have a reasonable physical interpretation if you apply them on an equilibrium state. So the state you were talking about is out of equilibrium. There's a washing machine or refrigerator or whatever outside, and it's not in an equilibrium, right?
There's an equilibrium state. I mean, there's a mirror is the opposite of the black hole.
Yeah.
There's an equilibrium state. I think the construction has to be modified.
So the mirror, you mean, I'm using the word equilibrium a little bit as the same. I'm identifying equilibrium states and typical states here. So the state you're talking about would not be typical in the space of states of that energy, right?
Sure.
Yeah. So I can give you an answer by starting with the equilibrium state on top of which you have added those mirrors. But yeah, it's not entirely satisfactory, I think.
The reason that I'm saying that is the Minkowski space that I'm talking about. Space-time. There's also saying as an equilibrium.
Yeah. So sure. So if you want to do the same thing for an evaporated black hole in flat state, it would be not trivial because the states are not really in equilibrium. They evaporate. So for now. radiation, and then we have the same quantum information in two places at the same time on this nice slice, and this is inconsistent with linear quantum mechanics. But then we discussed the possibility of avoiding this problem by postulating the idea of black hole complementarity.